Welcome to WOW TV. My name is Angel and I'm here from the Wizards of Wright program. The WOW program is a part of the Educational Outreach Office here at Wright-Patterson Air Force Base. Today we're going to learn about electromagnetism, which is a type of magnetism produced by an electric current. Are you ready to get started? Let's go. An electromagnet is a magnet that is created using electricity. Electromagnets are used to power microphones, speakers, headphones, some telephones, doorbells, computer hard drives, and even some household appliances. Magnets called permanent magnets can't be turned off. These magnets do not need electricity to work. As we will see today, the strength of an electromagnet can be changed by changing the amount of electricity that it is connected to. We will use some vocabulary words today, so let's make sure we all understand their meaning. There are many forms of energy, like wind energy, solar energy, and sound energy. Today, we will be using mechanical energy and electric energy. Mechanical energy is said to be the ability to do work. Mechanical energy is the moving energy or kinetic energy of an object, plus that object's stored energy or potential energy. Think of mechanical energy as movement. Walking people and rolling bikes are examples of mechanical energy. Running cars and moving gears in machines are examples of mechanical energy. Electrical energy is a form of energy caused by the flow of electrons or electricity. Electrical energy runs our computers and TVs and turns our lights on. We normally find electrical energy in a wall outlet or in a battery. Let's discuss the difference between a motor and a generator in relation to these energies. A motor is a machine that makes power. It is an electric device which converts electrical energy into mechanical energy. The generator works in reverse. It converts mechanical energy into electrical energy. Let's take it one more step and talk about force and a magnetic field. The space around a magnet is where the force of the magnet is. This is called its magnetic field. A magnetic field can be seen when we draw the magnetic lines of force that begin on the north pole of a magnet and end on the south pole of a magnet. As I mentioned before, there is a difference between a permanent magnet and an electromagnet. Most of the magnets you are familiar with are permanent magnets, meaning the material is magnetic all of the time. However, a magnet can also be created using electricity. And of course, these types of magnets are called electromagnets. Electromagnets create a magnetic field through the application of moving electrons, or an electric current. Using this, we can generate an electric current. When creating an electromagnet, a current is introduced, either from a battery or another source of electricity, and it flows through a wire. The magnetic field is formed around the wire, magnetizing it. The magnetic field only exists when electric current is flowing through the coil and disappears when the current is turned off. Therefore, you can turn the magnet on and off by completing or interrupting the circuit. It's like magnetism on demand. The electromagnet that we will experiment with today is called a solenoid. Do you see the wire is wrapped around the metal rod? The atoms in the metal are arranged randomly, not pointing in any particular direction. When the current is introduced, the magnetic field will realign the atoms. This magnetizes the solenoid. When we turn the current on and the atoms are all moving in the same direction, the magnetic field gets bigger. The alignment of the atoms increases and decreases with the level of current. Therefore, by controlling the flow of electricity, you can control the strength of the magnet. When the current is turned off, the atoms lose their alignment and go back to sitting randomly. Fairly quickly, it loses its magnetism. In our example, the strength of the magnet is directly related to the number of times the wire coils around the rod. If we wrap the wire tightly, we get a stronger magnetic field because there are more loops for the current to travel through. Let me explain your first activity. Teachers, in a moment, please give one of the blue boxes to your student groups or pairs. Included will be one battery pack, a solenoid with the 3 wires already attached, a baggie of washers, and a donut magnet. The students will hook up the solenoid, the electromagnet, to the battery pack by following directions. Here's a few things you need to know. The red terminal is positive and the black terminal is negative. Electric current flows from positive to negative, and the battery pack contains 3 batteries in a series. Using the last plug makes the electromagnet strongest. The groups will need their student sheets for specific directions. The objective is for the students to experiment by lifting the washers, pressing and holding the power button, and then dropping them by removing power, your finger. We ask the students to compare the number of washers they picked up against the number of batteries used. I'll wait while you complete only activity number 1, which includes 3 tasks. When finished, they can put the solenoid, the baggie of washers, and the donut magnet back in the box. They won't be needed anymore. I'll meet you back here with the next set of directions. Now, let's take what we've learned about electromagnets further. We will use what we understand about the attraction and repulsion of that donut magnet, which is a permanent magnet, and the electromagnet, and discuss how a motor works. We're going to use a St. Louis motor, which is also called an induction motor. It uses the moving magnets and coiled wire to create an electrical current. It converts electrical energy to mechanical energy, energy from the battery to the motor. A St. Louis motor can also work in reverse. Electromagnets are an essential part of motors. A key principle of the motor is to cause continuous motion and change the magnetic field at the right time. Otherwise, the magnet would rotate once and get stuck. Teachers, the student groups or pairs will now need 1 St. Louis motor, 1 red double-ended alligator clip, and 1 black double-ended alligator clip. They should still have the battery pack from the first activity. They will use the alligator clips and battery pack to run that St. Louis motor. Their student sheets will have the specific directions on how. I'll wait while you complete only activity number 2, which includes 4 tasks. When finished, the battery pack can go back in the blue box and that can be collected. Please also collect the St. Louis motor and the 2 pairs of alligator clips. They won't be needed anymore after this. I'll meet you back here with the next set of directions. If you still have any of the materials out, please pause again to collect them. Using any of the materials from the first 2 activities with the hand crank that you're about to use can damage the crank. Both motors and generators use changing magnetic fields. Motors convert electrical energy into mechanical movement. This is kinetic energy. Generators do the reverse. They change mechanical movement into electric energy. Teachers, the student groups or pairs will now need 1 hand crank generator, 1 light bulb mechanism, and 1 bell mechanism. Let me explain the 4 tasks you'll be working on. First, you'll connect the leads of a hand crank to the one another group is using. Make sure you follow the directions on your student sheets as you do this. After that, you'll use the hand crank generator to convert mechanical energy to electrical energy. Turning the crank will produce an electric current and cause that light bulb to glow. Then you'll be using the doorbell. The doorbell is a good example of how electromagnets can be used in applications where permanent magnets just wouldn't make any sense. When a guest pushes the button on your front door, the circuit is completed. The closed circuit allows electricity to flow and create a magnetic field. The magnetic charge causes the metal bell and metal clapper inside to clang together. When your guest releases the button, the circuit opens and the doorbell stops ringing. This on-demand magnetism is what makes the electromagnet so useful. Your student sheets will give you the specific directions for activity number 3. Students, please be gentle with these cranks. When using the hand generators, it's natural to want to go as fast as possible. However, this can break it. Turn the handle at a reasonable rate, fast enough to observe what you need to test, but not excessively. As you are working, consider how the generator is similar to the motor you already used, and how is it different. I'll meet you back here when you have finished. Teachers, after collecting all of the materials, take this opportunity to review the vocabulary words we began this lesson with: mechanical energy and electrical energy, generator and motor, force, and magnetic field. And we can now add magnetism and electromagnet to our list. You all did a great job today. Thanks for joining me. And teachers, thank you for using this WOW lesson. Please check out more at our website at wpafbstem.com.